Using it like days. Thankfully, yeah, it's a lot better. You had they're very helpful. Yeah, I don't know what really expects. It's like quality life out of it. Yeah, we probably realize it's a little bit. Measure the one thing. I wish I guessed it. I measure the size.
Yeah.
We looked at something. Basically guessed it. Basically not a guessing. I just made it really high. Yeah, the way I like. So it's easy to.
We do. Oh. Ready for it.
Well, you guys.
Yeah, I do.
Good, how are you?
That's
It's the jump photo. I never noticed that.
But I don't know. That's why I just want to show, thank you. I just want to go to this office out of that.
We're in groups.
Okay, so let's get going. You got a couple of reminders here. So, reminder, midterm is coming up. It still will be a while yet, 2 weeks from Friday. And it will be up through last class. It won't include this class. We're starting a new topic today, and I won't include that, okay? So it's still a couple of weeks out because we, want to do this homework cycle. There'll be a homework cycle that will be on this work that we're going to do on Friday. There'll be a slug test, and that topic will be on the exam. So I want to go and do that homework and get it back to you before we have the exam. Right? It'll be up through last class. So you can see on the syllabus there's a double line on the topic. There's a project required for grad students, and it's going to be extra credit for undergrads. It'll start soon. The way that it's going to be done is that there'll be start off with a proposal. And that's coming up. I'm not quite sure when the deadline is. It's on Canvas. If we're going to do a project, what I would recommend is that you talk to me about it first. So grad students, you should do that. Just what I want to do is have you do a project that is doable in the kind of time frame, but also relevant. So it should be something related to the things that we're doing in the class. So primarily related to groundwater. A lot of times people do things with some of the models that we've been working on. A nice topic is to take the models we've been working on like one step further than what we've been doing in class. So there are a variety of things that you can do along those lines. It will be extra credit for undergrad, and I just realized this is coming up, so I've been in touch with the people at Canvas to figure out how to put it into Canvas so it's kind of formally in there, so you can see like how many points it's worth. It's a little bit tricky because everybody's lumped together, and some of you are required to do it, and some of you are optionally going to do it. So how to get Canvas to recognize that, I'm not quite sure, but I'll figure it out. Okay, so that's coming up. And coming up next time is going to be this field class where we're going to be down here at the well field. We'll meet there. It'll be the regular class time. So keep that in mind when you're planning your I don't know, walk over here. The way it's going to work is that there'll be I'll tell you about slug tests and I'll show you how to do one. I'll show you the equipment. We'll have to measure the water level, depth to water. Remember, you've had to use that in calculation, the depth of water. I'll show you how to make that measurement. And then for the assignment, you'll need to come back and do the slug test yourself. Okay. So it'll give you opportunity to go and use this gear and make measurements yourself. And the way that it's going to work is we'll break up into groups, and I've assigned these groups here just to make it simple. And so what we want to do is identify a time when each one of these groups can come and do the test. It'll probably take an hour or so. And we don't want to have the groups like right back to back, because when you do a slug test, the water levels will be changing, and you don't want to have somebody you don't want to have another group coming in right away. But as long as they're separated by an hour, that should be fine. Okay, so one of the things that would be good to do, yeah.
So if I have a class right after this, do I need to tell them I might be late or like might not come at all?
Oh, you'll come.
Okay.
Where is it? I mean, can you walk
Yeah, I mean,
there from here to there?
Yeah.
Yeah. We'll cut it at 12:05 and take off for sure. Yeah, it'll be good. Okay, so one thing that would be good, maybe after class, go and say hello to the group members. Some of you may know other people in the group, but it would be good to introduce yourself. And if you want to start figuring out a time when you can all be there to do it, that'll be good. Maybe then when we meet in class in the field, we can do some scheduling to make sure there's no overlap. So maybe try to find maybe 2 times when the whole group can make it. Okay, and then we'll get a time when a unique time for each group to come. Okay, I'd like to. This has gotten pushed back a little bit, so the homework for this is due a week from Friday. So normally we would have done this on Monday, and you would have had all this week and next week to do the field work and then also work it up. So now we're going to be short some time. So I'd like to keep it still due on Friday so I can have time to grade it and get it back. If things get pushed, with your schedule, then I'll push the due date back a little bit. But because I want to get the homework back before the exam, rather not push the exam back. So we'll play that by ear, but right now we'll be targeting getting the homework done by a week from Friday. Okay, any questions on that?
So Friday, we're doing the procedure for slug
Yes.
testing, and then before next Friday, we have to get together with our group, run our own tests, and then analyze the data before we meet next Friday.
That's right.
So will you give us the materials we need to do the slug tests on our own? Water,
Yeah.
water tape and all that stuff?
Yeah. They'll have all that and instructions and have
So
all.
you won't be there with us when we're doing our slug?
I won't be.
Okay,
No,
that's fine.
no, you're gonna, I'll be on the phone. You can give me a call, but yeah, you'll need to figure it out yourself. But we've done this many times. You can figure it out. It's good. Yeah, one thing too that we'll need to do is we've got the gear But we'll need to pass the gear from one group to another. Okay, so some of the gear we can leave out there, but the water level meters, I don't want to do that. So we'll have to figure out that logistics. Okay, so when we figure out the order, we're gonna need to figure out, you know, who hands it off to who and how that's going. Okay, it's doable. Done it before, but it, you know, it just some stuff we'll need to plan for. Okay, so well stuff. Okay, so we're gonna change gears a little bit. What we've done so far in the class is we started out with kind of some big picture stuff. We learned about flow through porous media under saturated conditions. Learned about water table and contouring the water table and flow nets and how to analyze flow in saturated conditions. And then we spent a bit of time working with wells and how to characterize aquifers. So what I want to do now is go from aquifer up above the aquifer and look at what's happening in the beta zone. So we're still in the subsurface, but we're going to be above the aquifer, and looking at how to think about flow and storage of water in the beta zone. So there are a bunch of reasons why we might be interested in this. When we have rainfall. Oh, and by the way, the weather looks like it's going to be good on Friday. It'll be sunny. Should be partially sunny tomorrow and then sunny on Friday. And it's a high of like in the 60s, but I think in the morning might be cooler. So check the weather, maybe bring a jacket. Also, it's in this grassy place, and the grass it's places where the grass is a little bit high. So it may still be wet. So just keep that in mind. I don't know. I'm going to bring some waterproof shoes. It may not need it. It may be just dried out, but it you know, just as a heads up about that. So yesterday we had pretty good amount of rain, right? And so what happens when it rains? We'll see more about this, but what happens when it rains is the rain falls, and some of the water that falls as rain infiltrates into the subsurface, and some of it flows downhill. And the partitioning of the rainfall between infiltration and either overland flow or interflow is going to play an important role in flood, because this rapid rise of the water is from this partitioning or this component of the basically the hydrologic cycle. So if you have the rain getting partitioned into infiltration, then it goes into the subsurface and it makes its way to stream slowly. And you have base flow and modest changes in water level. But this component is much more rapid, and that will lead to flooding. So if we're interested in surface water, then we'll also be interested in how and the role that flow in the beta zone plays in creating floods. So most agriculture is going to be grown the plants will be grown in the beta zone. So the flow of water in the beta zone is going to be really key to having successful crops. You want to have the water should be stored for long enough so for the crops to utilize it over some time period. You don't want to have the water go through the soil very rapidly and have very little storage, because then the crops don't have a reservoir to draw on. You also So you don't want it too permeable. It was, if you had this very clean sand, you don't have crops growing on that too well because the water will go through it very quickly. On the other hand, if it's really low permeability, then the water hangs there and it stays saturated for a long time, and you don't get oxygen into the roots. So those two end members are going to be poor for growing crops. And then you want a grain size distribution kind of in the middle. A loam is going to be the ideal case, and that's kind of a broader distribution of particle sizes that will hold the water, but it'll also allow air to get in and oxygenate the roots. So the details of flow in the vadosome are going to be really key to agriculture. Almost all contaminants are going to start out either at the ground surface or in the shallow subsurface. And typically they're going to start out in the vadosome. We're going to either put them there intentionally in some kind of a tank, or they'll be released from some kind of containment, and they're in the vadosome first. So in some cases, they're going to migrate, they'll flow or get transported through the vadosome and into the saturated zone and form a plume. And that'll be a problem that we'll have to deal with, and we'll see a lot more about that later on in the class. But it's going to start out with the contaminants in the vadosome. So sometimes it'll reach the saturated zone and form a plume, but pretty much all the time, the contaminants, when they're released, they'll be in the vadosome. So we'll have to understand how contaminants are moving in the vadosome and how we might be able to remove them or break them down in the vadosome. So that'll be a key. Yeah, this is kind of a classic place where they were storing these old drums full of nasty stuff. So then there's this place. Anybody recognize that place? No? Anybody heard of Yucca Mountain? So Yucca Mountain, it used to be a lot better known than it is now, because Yucca Mountain for a long time was the high-level nuclear waste repository that we as a country were going to use for our nuclear waste. They spent a lot of effort understanding the site, and then the political winds changed, and they decided that they would not put it there, and they would do something else. And it's not clear just what that else will be. I think they're still working on that. There have been some discussion lately that maybe they would consider going back here. What this is there's this ridge, and you can tell it looks pretty dry, right? Pretty dry. I don't see anything growing. So this is in Nevada, in a very arid place. And this is a ridge, and the water table, it's very arid. So the water table is deep. Water table is several hundreds of feet below ground. And the idea was that they would take the high level nuclear waste and put it down below this ridge, about halfway down below from the ground surface to the water table. So it would be deep, but it would still be way above the water table. And they would put the nuclear waste in there. It's very arid, so they would expect very little water to encounter the nuclear waste, and then if there was some kind of release, it would still be a long way to go to get to the water table. So the properties of flow through the vadosome were really factored highly into the selection of this site as as a as a good candidate for storing nuclear waste. Okay, so here's what I want to do, talk about the conceptual model of infiltration and flow in the vadose. How do we characterize the vadose flow properties, and then how are we gonna go about simulating it? So what I've got here is this is a pit that was dug in the site of an experiment that was done where there was a ring that was pounded into the soil, and it was right here. And then let's draw it out. So there was a ring that was driven in like that, and then it's sticking up like this. And here's the soil. And then put in some water, and the water has some blue dye in it. So we look at it just in cross section over here. Here's the ground surface, and here's this ring. And so there was some water put in here, ponded up at the ground surface, and it's infiltrating. Okay, so it was the lower level, usually when you do this, is kept at the same level, and the water then infiltrates. So you can imagine that after a certain time, you have the water is infiltrating down to that point, and it's saturated here, then it's going to be saturated in the subsurface, and you have this zone is saturated, and it ends up dyed. So this thing here, this leading edge is called the wetting front. And you can see here at the end of the experiment, the wetting front is right around here. Okay, that way a little bit better. Get the resist writing on the screen, but it's right in here. Okay, there's the wetting front, and it's gone down about a foot, I guess. So that's the main thing that's happening. What you can see is also happening is you see that this right here, these are dyed columns that go down. This one goes pretty solid down about here, and then maybe there's some blue dye there. So these are preferential flow paths that the water is following. Probably either there are cracks, or there are channels that are formed by roots that have gone down and penetrated deeper. And so you can see some of the water is flowing more rapidly than just the wetting front. Some of it is moving, maybe twice as deep as this, but it's a much lower mass going through these preferential paths. So if you're concerned about where the zone of saturation is and the main mass of water that's infiltrated, then that's going to be defined by this wetting front. But then we also have preferential paths where some of the water is going much more quickly. So if you're concerned with contaminant migration and how rapidly contaminants might make it down to the water table, then there are really going to be two rates of advance. The rate at which this wetting front is moving, and you've got a large mass. But then if you're concerned about just when some contaminants arrive, we see that the preferential flow paths are conduits where the contaminants could move much more quickly than they would in this wetting front. Okay. Yeah.
Does this help with your conceptual model? You can't get any actual data from this kind of experiment, or can you? But all I see is preferential flow paths, like you said, but I don't know how you would measure. pull actual data from that.
Yeah, so, I mean, one of the things that's done with experiments like this is to get just the bulk infiltration rate. And see how that changes with time. And you're not really concerned about this per se. Okay, but then, I mean, if you're interested in contaminant transport, then you would be interested in this, and you would want to see like what the spacing is and how far the dye is making it out in front of the wetting front, things like that. But it would be difficult things to measure without excavating it.
Yeah.
Right. Okay. So we'll take a look at some conceptual models here. And so the plot here is volumetric flux as a function of time. And what I want to do is introduce a concept of the infiltration capacity. So this will be the flux in. Here's a cross section. There's the ground surface, and then this curve here is we'll call it the infiltration capacity. Infiltration capacity. So that's the maximum rate that the water could infiltrate. And we start out with the soil here in a dry state. It's been a long time since it rained. So the capacity to infiltrate is pretty high when we start. Okay, now, since it's just a conceptual model, we'll keep things simple, and we'll plot here the rainfall. And rainfall is often represented using this kind of a histogram approach. So, you know, the rainfall that we had yesterday, you might see something like this. Okay, this is called a hyetograph. And this will be a flux averaged over, you know, maybe that's 1 hour. So this would be like inches per hour as a flux. And basically what it's going to do, you know, the rainfall rate is changing with time. So to characterize the flux, you average it over a certain time period, and you have the, you know, starting out slow and then building up and changing with time. Okay, so this is what a real rainfall would look like. What I'm going to do is take a simplified approach and average it. I mean, we can take just like one of these blocks and think of it like that, or we could just say I'm going to average it over this whole time, and just instead of having it varying with time, I'm just going to say, you know, it looks like that, one block, one average rate over the whole time. Okay, so that's what this is. This is just a rainfall rate at this rate over this whole time. Okay, very simplified rainfall. So what happens when the rain starts out is the infiltration capacity is greater than the rainfall rate. So as the rain falls, there it is. So as the rain falls on the surface, it's gonna all infiltrate right here in that time period. And so if you're out in the woods and you're walking around, or let's say you're out in the woods, you know, you have interception. So let's say you're out in a field and it starts raining, you know, you look down and you're not really seeing any water because everything that falls is infiltrating. But as as that happens, the water content of the soil is increasing. And as it increases, the capacity for infiltration is going to decrease. So this change in the infiltration capacity is occurring because the soil is getting wetter as it rains. And then at some point, the infiltration capacity becomes equal to the rainfall rate. And then when it surpasses that, then we've got the capacity for infiltration less than the rainfall rate. So what this means is that if we think of it, you can think of it as a control volume there, right? And so if the flow into the control volume is greater than the flow out is the infiltration capacity, then we have to have some water stored in here. Okay, so what happens when we've reached this point is that we start to get water ponding at the surface. And got a little water. Okay, so this would be ponding or overlaying. Okay, so we reach this point, we start to get ponding and potentially overland flow. So this is the rapid flow that would go downslope and accumulate in streams. And this then, the hatch part is what's going into the subsurface. This little piece is the is going as the overland flow. So then we continue on. Okay, so here's the graphic, there's the rain, and we got some infiltration coming in the graphic over on the right. There's the wetting front moving down. And so as this is happening, this is the depth that the water has reached, and the water content here is increasing. And it keeps going, keeps increasing. And then when it gets high enough so that the water content here at the ground surface is saturated, the soil here is saturated, then we start to have ponding here. So the rainfall rate is greater than the rate at which the soil can infiltrate, and you get ponding building up there. And so if you're out walking around and the ground is flat, you start to see puddles forming, right? That's I think a common thing to see, but I don't know. I didn't really realize it at first, but I didn't really think about it at first. But in order to have the ponding, you have to have, or puddles, you have to have a rainfall rate that is greater than the infiltration rate. Now, it's going to form ponds if the ground is flat, or you've got some closed basins that form a puddle. But if it's a slope, then you have overland flow. Like so. So then the rain stops, and in our simple model here, the rain is stopping, and overland flow is stopping abruptly. It's a simple model. But then what's happening over here is this is stopping, but this process is continuing. So what will happen after the rainfall is the wetting front will continue to advance, and it's going to do that by moving down, and then the water at this moment, there's no water here. There's no infiltrating water here. This is partially saturated. When the wetting front moves down to here, then there's only this much water in there. So if the wetting front moves down here, then that means that some of the water that's here has to drain out of the pores. Okay, so you have the wetting front continue to move as it advances, the pores drain here. And the advance of the wetting front by gravity is slowing. And eventually it may stop or it may reach the water table. The table is down here. Okay, so if it makes it down to the water table, then that's recharge of the aquifer. If it doesn't make it down, then we don't have any recharge. What's going to happen also is as it's moving down, it's slowing down. And then we also have trees here with roots, and the trees are starting to bring it back out. Okay, so that will also slow it down and limit the depth that it can reach. So what we find actually around here is we've got rainfall that happens. I mean, on average, the monthly rainfall is about uniformly distributed through the year. In the summertime, when we have this going on, the trees are active and they pull out the water at a fast enough rate, so the wetting front rarely makes it down to the water table. So the recharge that happens around here is typically in the winter time when the trees are less active. So when we have big rains, and the trees are still fairly active now, but that big rain that we had yesterday that lasts all day, that's the kind of thing that would make it down deeper to recharge the bottom. Okay, so there's some ET happening, recharge may happen. Okay, so the stuff that's going on in the native zone is closely or has some important interaction with the saturated zone and the extent to which recharge occurs. All right, so there's some concepts. What we want to do is come up with some advance these concepts that we can then use for doing some modeling. So if we want to analyze flow in the native zone, Darcy's law, we spent a good bit of time so far thinking about Darcy's law, utilizing it for various applications. And, you know, fortunately, it's gonna be okay. Darcy's law will hold, and we can use those same concepts where we have the hydraulic head gradient is going to be proportional to the volumetric flux. Okay, so that's good. We're going to need to revise concepts of hydraulic conductivity and storativity, though. So those concepts will still hold, but we're going to find that that both of those things are going to change with the water content of the soil. So as the water content decreases, the soil dries out, that's going to decrease. And this actually increase. Well, this will be larger in the native zone because we can fill and drain pores. And we'll also want to take a look at the concept of hydraulic head. It'll essentially be the same, but there'll be some different twists to it. Okay, so what I want to do to start out with hydraulic head is go back to this little schematic that we used when we first were looking at hydraulic head. So this is just a column of water, and it's sealed open here at the top, and the water just, you know, at this level, and there it's just sealed here, so there's no flow in this. The water is just a static column. Okay, so remember we said hydraulic head is for groundwater stuff, we just say it's got two components: the pressure head and elevation head. The velocity head we can ignore. So what we did was to draw here what we did for when we first did this, we drew in the, this would be the elevation head, starting at 0, here's our datum. Start at 0, elevation head is gonna just increase like this. And here, this would be, the water surface would be like the water table, right? So the pressure head is 0 here. And the pressure then would increase with depth, like that. So there's the pressure head. And we add those two together, and so that's H equals P over gamma for V. All right. Okay, so that's the way we did it for the saturated zone. And now for the beta zone up here, what we're gonna do is just extend these lines. So we're just gonna go up like that and up like that. So I mean, the elevation head, it's just, it's just the elevation above the datum. So it goes up like that. And if there's no flow here, then the pressure head has to go like that, right? I'm sorry, the total head has to be the same everywhere if there's no flow. So if the elevation head is doing that, then the pressure head has to do that. And so what we get from this is that this is 0. So the pressure head here in the beta zone is less than 0. Okay, here we're using 0. The atmospheric pressure is our 0 reference. So what this means is that the pressure head in the beta zone is less than atmospheric pressure. Go. All right. So that's one set of concepts. And let's also do another experiment. So we have a little cup of water here, and I'm going to take a capillary and dip it into this cup here. And we can think of this, maybe as like a small diameter glass tube. So there's a small glass tube, and it wicks it up. Sometimes when they have do blood tests, I know they have a little glass tube and it wicks the blood up there. You could also think about this as a paper towel. Paper towel will have some very small pores in it that will pull the water up. So if you take a paper towel and just dip it into the water, it's going to pull the water up, and it works with a capillary action. So you can think of that as just like a single pore in the paper towel. Okay. So we've got the water that comes up here, and it's now stopped. The flow is stopped, so everything's static. So the hydraulic head is going to be the same here and here. So I've got these 2 points. This is like right at the water surface, and this is going to be right here at this surface. So what we can say, because there's no flow here, is that H1 is equal to H2. The hydraulic head at these 2 points is equal. There's no flow. And then by the definition of hydraulic head is that it's the pressure head plus the elevation head. And I'm gonna have these 2 points. So I'm gonna have the subscript here, and that's the pressure. This is just unit weight of water, so it's going to be the same. The pressure, that means the pressure head at that point, and this is the elevation head. Okay, well, and I guess we can have this. H2 is going to be the thing here. Okay, so we picked this point here at a special point. This is like right at the surface. So since we can pick our datum to be anywhere, I'm going to say that's my datum there. So if that's the datum, then Z1 is equal to 0. And if it's right at the surface here, the pressure there is equal to 0. right? So P over P1 over gamma is equal to 0. So H1 is equal to 0. Well, H1 is equal to 0. That means H2 is equal to 0. So here's H2. So H2 equals 0 equals P2 over gamma plus P2. So what that means is that the pressure head is equal to minus D2. Okay, so what we saw with the last slide is that pressure head is going to be negative. And what we see here is that if it's in equilibrium, so there's no flow, the pressure head is going to be equal to the negative of the height above the water table. Okay, so this wicks up by 10 centimeters, and the pressure head here is minus 10 centimeters. Okay, so that I think works out just using the principles that we've seen. The question then is, okay, so here's also some terms. So this is the pressure head. This is how, and we've been using this, for a month or so now, right? And so some of the terminology would use pressure head. The people that work in this area, then the pressure head is always negative. So they have a term called soil suction and moisture tension, and these things just drop the negative sign. So for the people working on the soils, they'll often have the pressure be as it gets increasingly positive, then the soil is getting drier and the pressure head is getting increasingly negative. Okay, so we just need to be aware of these different terminologies. The capillary pressure is the difference between the air pressure and the water pressure, and I'll show you how that is. That's also a case where the sign is flipped, and same with the matrix tension. So these are all terms for essentially the same thing, except the sign is it can be different. Okay, so I want to show you how this ends up happening. It's kind of peculiar that it ends up with this negative pressure. So what we want to do is to take a look at how that is working, and I'm going to go and blow up this region right in here, right around point number 2. Okay, so here's the capillary, and it's got a curved meniscus like that, and this is water here, and this is air. Okay, so what happens is there's you look at this interface, there are molecules of water here, and molecules of water are attracted to other molecules of water, and they interact. But right at the surface, there are molecules of water that are next to one another, and they interact with their neighbors. And that one right there, interacts with a molecule, its neighbors, and a molecule back there, but it doesn't have any molecule up here of water to interact with because it's right at the surface. So it's going to behave differently than molecules of water down here that are completely surrounded by that by other water molecules. Okay, so that gives rise to a surface energy, and the energy will depend on what two fluids we're dealing with. So for our applications, we'll have water and air, but it could be two different liquids that are like a water and oil, or it could be water and maybe some other gas. But the two different fluids will determine this interaction. So we have here this interaction described by what's called an interfacial tension. tension at the interface. And it's the energy per unit area of the interface. Energy, remember, is a force times a length, and the area is a length squared. So this interfacial area will use gamma sub I, and that has units of force per length. Okay, and that's, that, we can think of that as like the a tension pulling the surface here together because of the imbalance in the interaction between the water molecules across this interface. Okay, so that's going to form a key element to why we have this negative pressure in the data zone. And in order to do that, what we're going to have to do is balance the forces across the interface. So we're going to have a force here that's in the water, and a force here that's from the air pressure, and then a force that's generated from this this meniscus here. So remember, I think everybody probably remembers from physics that you can balance forces, and if something's in equilibrium, the force has to balance. So we'll do that, and we'll balance the forces across this interface, and that will give us a way to think about the pressure in the data zone. Okay, and we'll pick that up on Monday. So maybe if you don't know people in your group, if you go introduce yourself. Say hi, maybe exchange contact info.
Joey and Luke, what's what's your schedule like on Friday?
On Friday, I'm kind of.
Anybody in group two?
Oh, wait, we can go like outside of Friday.
Yeah.
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 Okay.
Yeah, okay, I'm slow. So.
Great.
Water sustainability.
What else group are you?
Yeah.
Joey, you wanna? Chase,
Jenna.
Yeah. Monday's I don't know who else.
Get a Marie, right?
So I can just, I'll send out an email to you guys.
Yeah, no, excuse me. All right, you guys.